Hello, everybody. Welcome to the Powered by Researchers webinar series, where we host leading researchers in neurotechnology to get the latest developments and data in the field. So thank you for joining us. My name is Ryan. All right, cool. So we're super excited and honored today to be hosting Dr. John Downey. Dr. Downey is a staff scientist in the Cortical Bionics Research Group at the University of Chicago, which uses the Utah array to decode intended movements from the motor cortex of people with paralysis and provide sensory feedback through stimulation in the somatosensory cortex. This research is at the cutting edge of neuroscience and engineering and will allow people with paralysis to fully interact with their environment in a natural and intuitive way. So with that said, I'll hand it over to you, John. Thanks again for joining us.
Yep, thanks, Ryan. So today I'm going to talk about some of the work we're doing in the Cortical Bionics Group on how to build a more advanced brain-controlled neuroprosthetics. So there's a lot of things we're doing. This is just a subset of the projects. Let's get started. So all of our stuff is done with the Utah array, and I'll show a little bit more about how we implant that in a little bit. But our goals are to restore independence for people with disabilities. So in the US alone, there are approximately 180,000 people with tetraplegia due to spinal cord injury, and another 58,000 with a major arm amputation, which may benefit from a prosthetic arm that is easy and intuitive to control and provides intuitive feedback. We really want to focus on making sure that because we have access to the brain, that everything is very natural, so easy to control, meaning that they don't have to learn a new strategy or work really hard at it. They think about moving their arm and hand just as you or I would. That's how they control the robot. And intuitive, going back the other direction, means that sensations evoked by touch on the robot hand should feel natural and be located where the touch actually is, so that they're, again, not having to learn a new strategy for integrating this sensation with their ability to do motor control. And so in order to do all that, we think it's very important that we learn more about the sensory motor system. So this is where we're putting our electrodes. We have a unique opportunity here. So the people that we work with are paralyzed, but the cortex, the somatosensory and motor cortices remain intact. So we can learn about how that system works in the functional brain while we do these studies. And by learning more about that sensory motor system, we should be able to better mimic how it works naturally when we're using it to interface with this robotic prosthetic. All right, so knowing all of that, how do we decide where we put our electrodes? None of this works if the electrodes aren't in the right place. These are some methods that were developed out of the University of Pittsburgh, kind of continuously being honed, but Jennifer Collinger and Fong Liu out of Pittsburgh are the ones helping to drive this. So on the right, you see the result of a functional MRI. So we have our, again, paralyzed participants lie in the functional MRI. They watch a video of a hand grasping and releasing at set times, and they're instructed to attempt to move their paralyzed hand in time with the video. And by doing this, we can find the area of the brain that's maximally activated during attempted grasp. As you can see here in the first participant from Chicago, who we'll call C1, we see a strong activation on that precentral gyrus, the motor cortex, right there at the bottom of what we call the hand knob, which is often, for many people, is a kind of an enlarged area on the cortex there. The slightly more difficult imaging to do is to identify the location in the somatosensory cortex, which represents each of the fingers. And so we know, as many of you may be familiar with, the somatotopy in sensory motor cortex traces the body, starting with the leg up in the central fissure. And as you move more laterally, it moves up the leg, into the arm, and then eventually into the face. And what you may not be as familiar with is there's a very large section of that somatotopy is dedicated to the hand. And within that hand area, we actually see a somatotopy for the fingers. So we know that the most lateral portion of the hand represents the thumb. And as you move more medially, you get the index, the middle. And what we're showing here is that if for somebody that has an intact sensory system, you can do tapping or pressing on the fingers to evoke this activity in the sensory cortex. But many of the people we work with are deafferented, meaning that they don't feel, or at least don't naturally feel, the sensations in their own hand. So we had to come up with a way for them to evoke activity in the sensory cortex without the kind of more natural inputs. And so they imagine tapping their fingers on a table in a certain pattern, and we can then get these maps out of that. So we see here this map again from C1. In the red, we see the thumb, as expected, most laterally, and then we move up and we see the green index finger, the kind of teal middle finger, and then the purpley dark blue ring finger. And so now we have maps for where we want to put arrays to get hand motor activity, and where we want to put arrays to get to evoke the sensory activity in the fingers we want. And so you can see here we have one motor array down near the area where the hand activity is maximal. And we have one motor array further medial to that to capture upper arm activity so that the hand can be moved to the correct location in space. And then over here, we picked locations for the sensory arrays that would allow us to stimulate in areas representing multiple fingers. So these arrays are cut down slightly from the standard 10 by 10 Utah array. So they're about 4 millimeters by 2.4 millimeters. There are finger representations which could subsume an entire array. We'd like to be able to provide information to multiple fingers, so we targeted the borders between these fingers to try to achieve that. So we see here that we targeted this one at the border between the thumb and the index finger, and the more medial one we targeted at the border between the index and the middle finger. And we have our surgery, and so our surgeons here at the University of Chicago are Drs. Peter Warnke and David Satzer, and they did a great job of putting everything up. And intraoperatively, we can take pictures of the cortex to compare to the structural image we got from the MRI. Here you can see these black lines are connecting some of the more obvious topological features to make sure that we've oriented everything properly and where everything's overlaid. Once those electrodes are placed, we can use the same map to show where the final inserted electrodes are compared to our initial plan. You can see here we managed to get quite close to our initial plan. The motor arrays being one for the hand and one for the more upper arm, and the sensory arrays being pretty much exactly where we initially planned to put them. Okay, so with the arrays in these areas, they're where we wanted them. So now we need to talk about what we do with these arrays. So the first thing that we've done, and this goes all the way back to our first surgery in Pittsburgh in 2012, is the motor control of the hand and arm. Some basics here. The electrode tips should be near a couple of neurons. And when we record the electrical activity from the brain at those electrode tips, we can identify waveforms that represent the action potentials of individual neurons. For our purposes, we treat each electrode as a single information source. So regardless of how many neurons it's recording from, we just run a threshold and count it there. We use those firing rates to control the arm, and we control that arm in set dimensions. The hand needs to move in space. The robot arm moves in the X, Y, and Z coordinates to move the hand to the location that we want. So that's forward, backwards, left, right, up and down. And then the wrist orients the hand. So the wrist can roll the hand, pitch the hand up and down, or yaw it left and right. Finally, we give them, in these cases, one-dimensional control over the hand. So all the fingers flex and extend together, like so. What does that look like? When we provide this kind of control to a participant, here the second participant at Pittsburgh, I'm going to try to do this through the PowerPoint so I can talk over it. Hopefully it won't too much. He can reach to and grasp a variety of objects. So you can see here the movements are fairly quick and fairly smooth, and he can grab the object off the left side of the table and drop it on the platform to the right without it rolling off. And so that's kind of a functional task that we use to measure the quality of the decoders. We have motor control now. We can move the arm in space. So what do we need to do next? We need to stimulate to restore sensation. So for example, you can imagine motor tasks that are impossible without the sense of touch. For instance, buttoning a button out of your vision, without being able to feel the button and feel the hole, that would be nearly impossible. But it turns out that even in cases where you might not think that touch would matter so much, it becomes very important to providing skilled motor control. So how are we going to provide that sensory feedback? So again, we go back to this schematic. We have an electrode tip that is in the brain near a number of neurons. And when we want to provide information to these neurons, so for motor control, we extract the information from the brain, we measure the electrical activity of the neurons. Here we want to induce information in the neurons by introducing electrical activity and causing them to fire. So we make stimulus trains where we put very small pulses of electricity at a set rate, often 100 hertz, into the brain, and then the neurons that are in proximity to that particular electrode should fire at least some of the times that those pulses hit the brain. Okay, and how do we organize this? So going back to our implant plan, we know that we have, again, for this participant C1, we have one electrode that should be on the border of the thumb and the index representation in somatosensory cortex, and one electrode that should be at the border of the index and the middle fingers. And if we break it out and we ask the participant, on every electrode we stimulate, we ask them, do you feel a sensation? And if so, where do you feel it? What we can see here through the color coding is that lateral array does in fact evoke sensations on the index finger. That's the red color over here on this lateral array representation, and a little bit on the thumb, as we had hoped by aiming at that border. And the more medial array, in fact, evokes sensations on the index finger in the middle as expected, and a couple of electrodes evoke sensation on the ring. So that gives us coverage of 4 of the 5 fingers, which is really what we were hoping to see. For other participants, so P2 and P3, the 2 participants at Pittsburgh that have had these implants, they also get coverage of the first 4 digits. You can see for P3, the sensations come up the fingers, not quite to the tips usually. And for P2, the first person to have these sensory arrays implanted, he gets sensations right at the base of the fingers, but covering all 5 fingers. And you can see, again, they follow the somatotopy as we'd expect, with the thumb being the most lateral arrays evoke sensations in the thumb, and then the index, and then we move up to the middle and the ring. And for this one participant, the pinky. Okay, so that's great. We've put the electrodes where we wanted them. They do in fact evoke sensations on the fingers that we were hoping to evoke sensations on. But the next thing to know is how reliable are these maps? So if somebody's reaching with their hand and they touch something with their finger, and one time they touch and it feels like the index finger, and the next time they touch and it feels like the middle finger, that's not going to be a very reliable source of information. And so to look into that, Charles Greenspun and Giacomo Valle here at the University of Chicago ran a study on using the fingers, so pressing the fingers and asking the participant C1 to tell us which finger was being touched or was no finger being touched. So we could touch no finger and ask him which one, and he should correctly report no sensation. We found that when we did this with a single electrode assigned to each finger, he was able to get it correct about 60% of the time. It depended, his accuracy depended on which electrode was assigned to each finger. So there was quite some variance there. But when we used multiple electrodes per finger, that increased his ability to tell which finger was being touched to nearly perfect most of the time. And then we can do an even more difficult task where we can touch no fingers, 1 finger, or 2 fingers. In that case, a single electrode assigned to each finger led to a lower but still well above chance level of performance. But when we applied multiple electrodes for each finger, we moved back up to nearly perfect performance. And so this is a sign that providing a strong enough input does make these very reliable sensations, and that picking the correct electrodes can greatly benefit the performance on a task where he needs to know which finger is making contact with an object. Okay, and so now I'm going to try to show this video. So this is going to be pressing on the fingers, or we press the palm, which has no sensors, for the null case where he shouldn't receive any sensation, and he should report what's being pressed there. You can just listen to the audio.
12. 13. 14.
Nothing.
15.
Middle finger.
16.
Thumb.
17.
Middle finger.
18,
index finger.
19.
So as you can see there, he can, reliably and usually fairly quickly tell us which finger is being touched. One thing that was funny to find out was that actually with him and with other participants, the mixing up of middle and ring is usually more of a cognitive thing. So they'll say middle and then think about it for a second and say, oh no, ring, that's why I felt it, the ring. So we struggle even with natural touch to say those words, even if we know right away which finger, we can tell which finger we felt. Now we have fairly reliable motor control where we can pick up and move objects. We have reliable sensory input where we know that we can stimulate an electrode and they'll feel sensations on specific fingers. And we want to do what we call closing the loop. So putting those two together so that they're controlling a hand and also feeling it at the same time. And so that looks like this. We record the activity for motor cortex that I've been talking about, represented here by spike rasters. The firing rates of those neurons in turn drive movement of the robotic hand and arm. That movement at times will lead to touch on the fingers, which will send force information back to the computers that can convert that force information into stimulus pulses that we send into the somatosensory cortex. So the person feels sensations as though they're coming from their own fingers. And then they can, once they feel that information, they can use it to then alter their motor plan, and the loop continues. So this is closed loop control. And what we want during closed loop control is to see an improvement in performance. So even in a task like the task I showed earlier, where we're grasping fairly large objects, they're all visible at all times. It's not something like a button that you can't see, but even with large objects, you would think that perhaps without sensation, you'd be able to do just as well because you could use visual feedback. In fact, we found that providing sensory information to a participant greatly improves their ability to do these tasks. And so again, I'm going to switch to a video here, I'm going to switch to a video here. Okay, so on the left, you will see the fastest movement for, so in each condition with and without stimulation, they were provided the opportunity, they were given 9 chances to complete a task with the object. Here I'm going to show the fastest of each in each condition. And you'll see that the best movements with stimulation consistently outperform the best movements without. So as you can see, they were very reliably faster with stimulation than without, largely because they felt more confident making the grasp attempts, knowing that they would have the ability to tell quickly whether the grasp was secure and where it was in the hand. And to put some numbers on this, here we have plotted the amount of time for every trial, so that's 9 attempts per object across 3 days, and there were 9 objects. So we see here in gray the time it took to complete those trials without the stimulation, without ICMS, intracortical microstimulation, and in blue the amount of time it took when he did have stimulation. And this was work done in collaboration with Charlene Flesher at the University of Pittsburgh. And what we see here is that the trials with stimulation were consistently faster. And in fact, if you look at that hashed bar, the very first bar, anything that happened during any trial completed in that time was considered a completely successful trial. So that's considered movements that are within the normal speed of the human arm in an intact condition. And we see that far more, nearly almost 20% of trials were that fast with stimulation, and only a couple of trials were that fast without stimulation. And in fact, the median time to completion without stimulation was 20 seconds, or 4 times as long as the normal completion time. And that was cut in half with the provision of stimulation. This result is wonderful. It shows the importance of closed loop stimulation, even in a task that might not appear at first glance to require that stimulation. Sensory information just makes grasping more easier and more trustworthy. But there may be one of the still outstanding questions at that time was, how does stimulation in S1 affect M1? We know that there are reciprocal connections between the two areas, and we know that because sensation is so important for motor control, the two areas must be talking to each other in order to properly coordinate these movements. And so in work that we did with Natalia Shulchkova, a grad student in Sleeman's lab, we found, in fact, that there is a noticeable effect of stimulation in somatosensory cortex on recordings and motor cortex. So here, in 2 participants, so notably P3 and C1, P2 was the participant who performed the closed loop tasks in the previous video. And it turns out, I'll just say here, that he has the least representation in motor cortex of stimulation in somatosensory cortex. So while he was still receiving the sensory input, the information provided by the sensory input, the stimulation that was providing that input had a more limited effect on our ability to decode from his motor cortex. But in these later 2 implants, we find that on the left, you can see 1 channel from P3 in green and 2 channels from C1 in purple that all respond quite strongly to stimulation. So we see no stimulation at first, and then under the black bar, we see stimulation turned on and then turned off again. And we can see that there's a lot of excitatory activity in motor cortex when electrical stimulation is provided to sensory cortex. We repeated this analysis with sorted units to rule out any sort of electrical artifact or kind of neural noise baseline change. And these are, in fact, individual neurons responding strongly to stimulation of somatosensory cortex. We also see the inverse. Different channels in motor cortex show a decrease in firing rate, inhibition during stimulation of somatosensory cortex. Again, 1 channel from P3 in green and 2 from C1 in purple. Given that we have 192 motor channels and 64 sensory channels, looking at all of the pairs in isolation is not a very practical way to understand this effect. So one way we looked to understand it was whether there was any sort of spatial component to it. And so as one type of analysis we can look at is if we look at just the activity here in the lateral motor array, seen with the asterisk on the left, we can look at stimulation on any sensory electrode. Here, if you look at up here, the lateral sensory array has this black dot. The projected field, where the person feels that stimulation on that electrode, is shown in green on the thumb here. And then all the other green electrodes also evoke sensations on the thumb. So we can stimulate each of those electrodes separately and then average the activity and motor array across all of those sensory electrodes to find an evoked map in motor cortex when stimulating the thumb area of sensory cortex. As you can see at the bottom, that evoked sensation is largely located on the lateral edge of that motor array. If we repeat the same process here for the ring finger, so the single electrode evokes the sensation drawn in green on the hand here. All the other green electrodes evoke sensations localized to the ring finger also. We then average the motor response to stimulation on all of those electrodes, and we found that the kind of posterior medial corner of the array shows the most activity during stimulation of ring finger electrodes. So that's an interesting map. We see kind of the movement across the array. So the thumb has kind of the bottom left corner, the ring has the upper right corner. And we were wondering if there was any more if there was a explainable reason for this spatial mapping. And so we asked the participant to perform a task where he imagined flexing and extending each of his fingers individually. And then we found the difference from the divergence from average for each finger. So whether a single finger increased or decreased the firing rate on a given electrode more than the other fingers do. And here we see those maps. So for the thumb on the left, the thumb flexion extension task saw excess activity on the lateral edge of the array, while the ring flexion extension task saw excess activity on the posterior medial array, the corner of the array. And if we compare that back to the sensory evoked maps, we see a very, very close spatial match. So this indicates to us that there is a very tight linkage between the somatosensory cortex and the motor cortex that respects the somatotopy of both areas. That is, the map in the cortex for both areas is tightly linked, with the thumb area of somatosensory cortex preferentially sending activity to the thumb area of motor cortex. Now that we have an understanding of the distributions of this activity, we also want to know how this activity is present during motor control. So if we're going to do this in a closed loop setting, the person is going to be attempting to make movements, thinking about those movements, and we're going to need to identify in motor cortex what their intended movements are, while also evoking changes in motor cortex due to the stimulation being provided. And so here we're looking at a task where the hand is still in space, an object appears, the person attempts to grasp it. This is all under complete computer control, but they know to follow along. They attempt to grasp the object. Once the object is grasped, stimulation is provided at one of 4 amplitudes, shown in the varying shades of orange here. And different motor channels respond differently to that during that time period of stimulation. So here we see channel 1 has a strong response to the stimulation, with high amplitude stimulation driving much higher firing rates on channel 1 than low amplitude stimulation. But in this task, channel 2 and channel 3 show no particular response to the level of stimulation. So we then do another task, which is a classic task for us called the grasp and transport task. So here they're reaching to a spot in space where an object is. Once they get there, they attempt to grasp the object. Once the grasp is completed, they'll then move the object to a new location. And finally, they'll release it. And so that gives us a couple of phases we can look at. So the first phase is the grasp phase, which should be the same as the squeeze task here, with the exception of it can happen anywhere in space where an object has appeared. So the hand isn't still the whole time, it's reached out, but once it's there, all it's doing again is grasping the object. Again, we see a similar response on channel 1 with the stratification by stimulation amplitude. Channel 2, again, shows no particular response to the stimulation. But channel 3 here shows actually an inhibition with increasing amplitude of stimulation. So that's interesting because during the solely grasping task, it showed no response, but when grasping during this other task, so the same motor activity in a different context evokes a different response to stimulation of somatosensory cortex. And now during the transport phase of this task, when the object is being carried to a new location, we again can look at how the channels respond to the amplitude of the stimulation. And we see channel 1 keeps on keeping on at the same stratification. Now channel 2 is responding to the amplitude of stimulation, while channel 3 has quenched its response by the time we transport. So these are obviously illustrative examples. These are real data, but there are 192 channels, and these are just 3 of them. But we do find that across many of the channels, we see responses that are dependent on the interaction between the stimulation amplitude and the intended movement. So this is, for purposes of decoding, going to make it difficult because we want to know the intended, we want to know which modulation of motor cortex firing rates are due to intended movement, and which modulation are due to the stimulation that we're providing by ICMS. And to the extent that those two interact, it makes it very hard to disentangle the intended movement from the activity that we're putting in. And so to illustrate this, in participant C1, We had him complete a grasp and carry task. So reach to an object, grasp it. Once the object was grasped, we started stimulating on a pair of electrodes. We then asked him to move the object to a new space and release it. And then the stimulation stops once the object's released. And at the top, we can see the percent of trials that were failed when there was no stimulation in gray or regular stimulation in blue. And we see that essentially he failed 12% of trials without stimulation and almost 40% of trials with stimulation. At the bottom, we see that during that carry phase, when stimulation is being applied, with no stimulation, the path length averaged just under 1.5 meters through space. But we can see a much higher skew in the linear stimulation, where the hand was not going directly to where he wanted it to go to, and he kind of had to fight it around. And so that led to a lot of our failures. So in a participant who specifically showed strong responses in motor cortex to the ICMS, while the sensory information can be very important to the motor control, the evoked response in M1 during ICMS and somatosensory cortex can disturb the ability to decode that motor intent. And so I'll come back to what we do about that in a little bit. But first I want to talk a little bit about sculpting stimulation. So we know that we have good motor control. We know that we can stimulate electrodes, which reliably evoke sensations on a given finger. And now we want to think about how do we make those sensations as naturalistic as possible? How do we make those sensations immediately interpretable and feel like we would feel with our own hands? This is work that, again, was spearheaded by Charles Greenspan at the University of Chicago. The first thing to do was to take a result that we had already found with the first participant at Pittsburgh and check across 3 participants here. And that is that increasing the stimulation amplitude for the ICMS linearly increases the perceived intensity. So we ask the participant we stimulate them at a certain amplitude. We ask them to tell us how strong it feels. We then stimulate them at a different amplitude and ask them to give us a new number rating. And we say, if this sensation feels twice as strong, you should give us twice as high a number. And what we find is that, across the usable stimulation range, an increase in, say, 10 microamps has a reliable increase in the perceived intensity, regardless of whether that jump was from 40 microamps to 50 microamps or 70 microamps to 80 microamps. So we see a very linear increase. We now, knowing that we have this scale, we want to be able to say, okay, that's great. We know that one feels stronger than the other, but how do they feel relative to an actual force on a hand? Because that's what we're trying to replicate here, is the sensation of the touch on the hand. And so for this study, we use participant C1, who happens to have mostly intact sensation on his thumb and index finger. We then use a force. So we use a mechanical indenter that pushes into the finger with a set amount of force. So you can see here it goes from 0.02 newtons to 0.27 newtons. And we ask him to report the intensity of the sensation on the finger. We then do stimulation in the brain in an area that overlaps with where the mechanical indenter is touching the finger. And we ask him to report on the same scale how strong that sensation is from the stimulation in the brain. And we see that the mechanical stimulation results in a logarithmic curve where differences at small levels of force give greater changes in intensity than differences at high level of force, while the stimulation provides a linear increase. We can then map these two to each other. So we map the force on the finger to the stimulation amplitude in the brain. And here this green equivalency curve is for the example on the left, and the gray is for a number of other electrodes. And we see that depending on the electrode, we have different slopes, and we cover different levels of force, but we can generally map a reliable mapping between the stimulation amplitude in the brain and the perceived force of the touch on the finger. And so now we want to think about how precise are these sensations? How precise are these sensations, and so how many different forces can somebody differentiate from a single electrode? To do this, we need to think about, how much do we need to change the amplitude for the person to reliably report a difference, for them to notice the change? And so we can do some psychophysics here, where we stimulate at 60 microamps and at another amplitude, the comparison amplitude, and ask them to tell us which felt stronger. And so plotted here is example electrodes on the left, example electrodes, one each for the 3 participants. And so the steeper this curve, that is, the more sensitive the person is to changes in amplitude. So here we can see, so stepping from 60 microamps to 54 microamps, participant C1 in purple is fairly likely to be able to tell you the difference. And so we use this to quantify the just noticeable difference. That is, how big of a change in amplitude do you need for the person to just barely notice that it has changed? And we see a number of electrodes in the different colors for the different participants here, plotting that distribution. So we know that different electrodes have different sensitivities, but many of them are down in the kind of, 10 to, the sort of single digits and low double digit microamp differences. So with just noticeable differences, we can talk about the number of levels of stimulation we can provide. So we need to know the detection threshold, the minimum amplitude at which the person can report it. And then we divide the difference between the detection threshold and the maximum stimulation amplitude we can provide, which is 100 microamps. We divide that by the just noticeable difference to get the number of discriminable levels of stimulation we can provide. And again, we have an example electrode for each participant here. And you can see that they vary between about 4 and 10 discriminable levels in these examples. And if we plot all of the example electrodes, we see that we can get, kind of somewhere between 2 and 12 discriminable levels with a median around 4 discriminable levels per electrode. For comparison, if you do the same kind of analysis on the actual indenter force, you get nearly an order of magnitude higher, you get around an order of magnitude more discriminable levels. So if we're going to try to match the capabilities of the intact finger, we're going to need to find a way to improve on the step size. And so one thing to think about is that up to this point, everything I've shown you has involved stimulating in a linear fashion, which is to say the amplitude of the stimulation has been proportional to the force being exerted. And so if you exert a force, it ramps up quickly, it holds consistent across the time the force is applied, and then it drops off as you release the force. However, we know that if we look at some previous work from the Bensmeier lab in monkeys, they applied a ramped up force, then held it constant for a while, and then ramped it down while recording from somatosensory cortex in the monkeys. And you can see these rasters show that there's a lot of firing during the ramp up, and much less firing during the static hold period, and then they fire rapidly again during the release of the force. And so that can be averaged out to a response trace that looks like this. An initial transient epoch with much higher firing rates than baseline, a sustained epoch with firing rates that are higher than baseline but much lower than the transients, and then a transient release phase as well. And so we propose recapitulating this pattern in a slightly simpler version where we do a 200 millisecond onset with a variable with a high force level matching the level of the linear force. We then lower the amplitude through the hold phase of the force to a much lower level, and then finally go back into the transient high phase on the release to attempt to evoke sensations that are more natural and more natural. And the result of that more natural style sensation is that the people are more sensitive to changes in the amplitude. So if we compare the peak of that transient phase to the linear amplitude, we find that reliably many electrodes are more sensitive to changes in this biomimetic stimulation amplitude than they were to the linear stimulation amplitude, which in turn gives us more discriminable levels, nearly doubling the number of levels that each electrode could differentiate between. So this is a big step towards more natural sensations and more interpretable sensations. Now, what about closed loop? That's great that we have more natural sensations, but how is that going to help closed loop? Well, it turns out that a secondary effect of this lower static stimulation amplitude is that less current overall is being injected into the brain for the same amount of force being conveyed. And so we were wondering if that might lead to less evoked sensation in motor cortex and therefore an easier time decoding it. And in fact, that is what we found. By using these biomimetic stimulus trains instead of the linear stimulus trains during a closed loop motor control, the failure rate returned to about the same level as the no stim condition. The path lengths during the transport phase of the grasp and transport task returned back to about the same level as the no stim condition. And so we find that the performance during no stim and the performance during biomimetic stimulation are not significantly different from each other, but the participant can still receive that stimulation of the sensory information that they need to do better closed loop performance, like I showed earlier. As I said, that was, I think I covered quite a lot here, but that's only a small portion of what we're doing in the Cortical Bionics group. Here I'm listing the people that contributed to the things I showed today. The team is much larger than that. You can check out our Cortical Bionics website if you want to learn more about the team at large. And of course, the most important members of our research team are the participants who volunteer their time and their bodies to these studies. Having worked with most of these people, they're all very enthusiastic and excited to help push science forward and to help people who have similar disabilities in the future who will hopefully benefit from these neuroprosthetics. All right, so if anybody has any questions, I can take them now.
Great presentation. Thank you, John. Really appreciate that. It's really amazing to see this stuff. A lot of us in the BCI field and who work, have a good understanding of these applications, but it's really cool to see the videos and see these applications in live time. So thanks for sharing that. Great. So we got a bunch of questions coming in. We'll go ahead and start from the top. So the first question is from Patricia, and she asks, how do you account for the adaptations that might occur in the brain after paralysis or amputation?
Yeah, so that's an interesting question. When we started this work, there was a lot of doubt about how well it would work. So a lot of the early work was developed in non-human primates that were fully intact. And so people weren't sure if the motor activity would be similar after years of paralysis. But I can say that we worked with a number of participants now who have all just kind of naturally thought about moving. We've seen activity that very closely resembles what was measured in non-human primates. And so it doesn't appear that it doesn't appear like there's enough plasticity or changes, wholesale changes to motor cortex to remove these patterns that we expect to see. So we worked with C1, who has good motor control, was injured, I think, almost nearly 30 years before the surgery to put the arrays in. So, yeah.
Wow, that's awesome. Awesome. Yeah, the next question is from Mateus, and they ask, did you use single units only for training the decoder, or did you also use local field potentials?
We used thresholded channels only. So we didn't use local field potentials, but we also didn't sort units. So anything that crosses the threshold on a given channel is counted. And so each channel is recording likely a number of neurons at various levels of discriminability. But we don't sort, but we also haven't used field potentials.
Got it. Thanks. Next question is from Nathan. They said, thank you for the presentation. Did you experience any complications or side effects of the electrode implantation?
Nothing. I mean, the electrode implantation has not caused any harm to the people, if that's the question. Part of their enrollment in the study is that their hands are they're not usually using the sensation or have no sensation left in the hand. So if there were to be a complication, it would not have a substantial effect on their daily life. But there's been no reports of any changes in that. So yeah, no side effects as far as we can tell.
Okay, great. And James sort of has a question / suggestion. They said it seems like maybe a continuous square wave rather than just a start and stop might be more effective in keeping the neurons firing and allowing for greater discriminability.
like a continuous amplitude. So there's limitations on the amount of current you can pass through an electrode at any given time. So I kind of glossed over this, but the pulses we send are actually balanced. So we send a negative deflection and then a half as high, twice as long positive deflection so that we balance the current on the electrodes. And if you do anything that resembled a DC offset, you would start to damage the electrodes and they wouldn't last very long. So that's why we do pulses.
Great. Yeah, that makes sense. All right. Yeah, another question from Kartik. They said, great talk. What is the onset latency of M1 response post-stimulation of S1? They kind of elaborated more. Is there any chance of stimulus artifact obscuring some of the early components of the neural response?
Yeah, so there's a lot of details in the bioRxiv paper on this. You can check the Shelchkova and myself. Yeah, so anyways, you can look that up, but the short answer is we send for a subset of these responses, we see a strong response that is time locked to the pulse at between up to 6 milliseconds after the pulse, we see the response. It is possible from some of the animal literature that there are sub 2 millisecond responses. We blank out our recordings during the actual pulse, so we can't see anything that happens before about 1.6 milliseconds after the stimulus pulse. So it's possible they're there and we're missing them, but I think we're probably capturing the bulk of them in that 2 to 6 millisecond window. And then I'll say a lot of the responses that we see are not locked to a single pulse. They're kind of shifts in baseline during the whole firing train. So that would not, we may lose a couple in the blinking window just because we could miss any action potentials in the blinking window, but they don't, much of the response is not directly tied to individual pulses, but rather a potentiation or suppression due to the continuing stimulation.
Great. I think you just answered that next question as well. So let's go to the next one. What kind of training programs do you take the patients through to imagine a movement that they can no longer make?
Yeah, as these things go out to more participants, a structured program may make sense. Up to this point, we kind of just talk to them about it. Each person has a different ability to sort of imagine this. They each have different levels of injury as well. So some of the participants have had no ability to move their arm whatsoever. They tend to find it a little easier. We just tell them, try to move your arm. And there's no chance of it actually moving, so that's an easy thing for them to do. Others still have varying levels of movement available in their arm, and so they just kind of have to work through thinking about moving their arm, thinking about how they would move their arm without actually doing it. And it's been a different process for each person, so there's not a single answer.
Yeah, makes sense. There's a lot of variability. Great. Yeah, and next question is from Rex. They said, fantastic stuff. Do the participants notice a qualitative difference between constant or biomimetic stimulation? So do they report biomimetic stimulation feeling more natural?
So they do tend to notice the difference on most electrodes. Different electrodes they can notice the difference in different ways on different electrodes, so this starts to be a complicated question, but yes, in general, they tend to feel that the biomimetic ones are more natural. But that can mean a different thing on different electrodes. It can be about the strength, it can be about the quality of the sensation. Yeah, it can vary depending on the frequency at which you stimulate as well, so it gets pretty complicated pretty fast.
Got it. Cool. We have a question from Alana. She asks, how quickly do participants take to using the system? Do they know how to use their prosthetics right away, or does it maybe take some time?
It can take a little practice. So one of the things we do is that we often train the decoders in the virtual reality environment, so they need to get used to having that as where they work, which for many of them is quite fast, but some of them take a little more getting used to. And then, yeah, typically the recordings take a little bit of time to phase in after the surgery usually, but once they phase in, they're usually pretty much off to the races. The motor control, they maybe get marginally better with practice, but it's pretty close to full performance from the start.
Great, thank you. Yeah, I guess a similar question from Mateus again. How long does it take to train the decoders each time before the session?
Yeah, it depends on the complexity of the decoder you want to use. So if we're using kind of the higher degree of freedom decoders, the ones that are closer to normal arm movement, that can take about 30 or so minutes, 30, 40 minutes at the start of the day. But then they work all day long, so we'll often do a 4-hour test session.
Cool, that's great. Another question from Jonathan. How is the mapping between spikes in M1 and specific arm and hand movements determined?
Yeah, so at the start of the day, so it's kind of on the same note, at the start of the day, we put them in the virtual reality environment. We have the arm perform a task that they recognize. So it's usually this grasp and carry task that I talked about a little bit. So reach out to the object, grab it, maybe reach out to the object, orient the wrist so that the hand aligns with the object, grab it, move it to a new position, perhaps reorient it, release it. And we have them attempt to make those movements as the computer actually controls the robot. We then, once we collect enough of these trials, we can then set up the comparison between the neural firing rates during all of that and the movements that the robot was executing. And that gives us the relationships we need for our decoder. There's then an intermediate step where we limit the errors they can make, but allow them to make the movements so that we get the timing correct. So you can imagine, if somebody was moving slower than the computer or faster than the computer, that can throw things off. So we then can adjust the timing. We repeat the task. We have them make the movements, but limit the amount of error they can make. And then we train the relationship again. And from then on, they pretty much use the decoder without any computer intervention.
Cool, great. Awesome. If it's all right with you, we've got more questions coming in, so we'll just keep throwing them at you.
Yep.
Another question from Jing. Have you, or maybe others that you know of, tried stimulating on multiple electrodes in the somatosensory cortex, whether that's simultaneous stimulation or rapid succession?
Yeah, so we have done multiple electrodes at a time. We've always done simultaneous rather than rapid succession, largely because of the blinking period I was talking about. So if we're going to use this for closed loop while also recording from motor cortex, we need to have as much motor data as possible. And so we do them, simultaneously. I mentioned briefly in the finger identification task that if we do multiple electrodes for each finger, so that can be up to 4 electrodes per finger, that makes the response more reliable. And yeah, there's more work to come soon from our group on what exactly doing multiple electrodes at a time does compared to a single electrode. But yes, we are doing that, and it does have some notable benefits.
Okay, great. Yeah. Really cool question from Craig here. He asks, does the stimulation ever evoke other sensations rather than just pressure, such as proprioception or temperature?
Yeah, so I talked about all these sensations as though they're pressure. They're not necessarily all pressure. So we ask intensity, which means strength, not necessarily exactly that it's force. Some of them do feel like pressure for sure. Some of them can feel like kind of a tingle or a buzz. Some of them can feel like, some of those stranger ones is like pressure coming from inside the joint. Like if you're, when you feel like your joint needs to pop, that kind of sort of pressure. We have not experienced any proprioception ourselves, although I believe Caltech has reported some proprioceptive sensations in their work, if I remember correctly. And yeah, so for temperature, we do get some reports of warm, although warm doesn't necessarily scale like heat per se. It just seems to be the closest thing they can get to a sort of unnatural sensation out of certain electrodes that they have. I'm not familiar with any reports of cold. And definitely one thing I didn't mention, but we've never had a report of pain. So none of the electrodes have been painful. We would expect pain to be processed somewhere else in the brain, so that's not super shocking, but it's good.
Yeah, that makes sense. That's really interesting. We got one more question here. We probably have time for one more. Let's go with Kate. She says, great talk. Are there any ideas on whether there is plasticity or spatial change in a cortical motor representation as a result of the individual training with the robotic arm? And she kind of elaborates, if so, how does that impact the complexity of the calibration at which you need to recalibrate the tools?
Yeah, that is a big question and not one that we have tackled rigorously in any way. So I will say that a couple relevant pieces of information. So one, we retrain every day because we see changes in which neurons we're recording from. So we don't always have the same neurons active. And I have a paper on this from, I don't know, a number of years back at this point, but if you want to see the numbers on that, but there's a pretty relatively rapid turnover in the number in which neurons are being recorded on any given at any given time. And so the same problem makes it very hard to measure any neuroplastic changes at the neuron by neuron level, because we don't have reliable recordings from those neurons to see how they change. So, if there were responses at more of a somatotopy level, we could probably find those. We've never looked closely, but we've never seen anything that has made us think we need to. So I don't think there's any large scale changes. This kind of goes back to what I was saying, that somebody that was injured for 30 years still appears to be using, the motor cortex still appears to work in mostly the same way as it probably did before their injury. So we wouldn't expect, a few hours, a couple of times a week to probably have a larger effect than not having use of the arm and hand for 30 years. So I wouldn't expect to see a change, but we haven't inspected closely.
I see. Cool. That's great. So unfortunately we're over time, so just end the Q&A there. If there's any other questions, we can probably get those to John via email and maybe get those back to you guys. So yeah, I just want to say thank you again, John, for joining us today and sharing your incredible research you're doing at with the Cortical Bionics Research Group.
All right, thanks, Ryan.